Today we are going to be talking about Isaac Newton's three laws of motion. The objective is to be able to understand how Isaac Newton's three laws relate to the motion of an object. So first, a little bit about Isaac Newton. This is a picture of what we think he looks like, and he discovered a bunch of things, and you probably know him best for the apple falling from the tree and gravity. He also did develop some telescopes, and he developed a law about universal gravitation, and we will be talking about that as well in this course. So he also did study motion, gravitation, math, religion, and philosophy. And he was a really influential scientist, and he is kind of the father of what started physics in the first place. So Einstein, he was the guy who started like modern physics and relativity and things like that, E equals mc squared. But Newton really focused on things much kind of more basic than that. So it was things that really helped us understand how our world works. And the two of them can go together, but Newton kind of started it. He wrote Mathematical Principles of Natural Philosophy, which described the universal law of gravitation and the three laws of motion. So just a quick side, there's a difference between a law and a theory. I'm sure you've heard this before, but just as a reminder, a law is kind of the what of our observations. It describes our observations. And in fact, one of Newton's laws is an equation. It's based on what we observe. And then a theory is the why of our observations. It explains what we observe. It explains those laws. And not every law has a theory, and not every theory has a law. Sometimes we don't know why things work. We just know that they do. And that's kind of why we have laws and theories and why there's a difference between the two. So these are both only models. They may or may not be the be-all, end-all. And in fact, some of Newton's laws get further explained by Einstein's laws. So you can use Newton as like a first pass, but then Einstein further develops it. So, for example, Newton's law of gravity describes the behavior that we observe, but doesn't provide any explanation for that behavior. But Einstein's general theory of relativity does provide the explanation, which is why it uses the word theory. So there's a huge difference between a common use of the word theory. So we use that as speculation or guess, sometimes even for hypothesis. And this is why in your labs, when you say theory and you mean hypothesis, I correct you, because the correct scientific use of the word theory is actually, it's not a guess. We know what it's actually supposed to be describing. So in science, a theory can also be a fact, such as the heliocentric, or the idea, the knowledge that the sun is the center of our solar system and not the earth. So, in fact, the word theory does not imply doubt, but it's actually an explanation, and it has the ability to predict things about what we're examining. Anyway, so for Newton's three laws of motion, we have the first law, and that is just that it's the law of inertia, and it says that objects in motion will stay in motion and objects at rest will stay at rest. And then this is only true if there is not an outside force that acts on these things. So what Newton's first law is saying, that there's something that keeps an object in motion unless something else acts on it. And really that something is the mass or the inertia. Mass is the measure of inertia that we're using for Regents physics. So then it's just another way of saying that things want to keep doing what they're already doing. So in something called dynamic equilibrium, which we will talk about a little bit later, it's everything is balanced while the object is in motion. So if it's at constant velocity, so it's the same speed, there's no acceleration, it's in dynamic equilibrium, and that just means that everything is balanced. All the forces in every direction are balanced while the object is in motion. So there's no acceleration. Okay, so for Newton's first law, as I said, it only has to do with mass. The more mass the object has, the more inertia it has. Then we go to Newton's third law. I know we're skipping second, but we'll get there. It says for every force, there is an equal and opposite force, and those forces must act on separate objects. So this is also known as action-reaction. And for example, we have a baseball bat hits the ball just as hard as the ball hits the bat. The difference is that the bat is so much heavier than the ball that the resultant motion on the bat is much less than the ball. So then a bug hitting the windshield of a car has the same force as the car hitting the bug. But again, there's a difference in that the car is much heavier than the bug. So the resultant motion of the car is much less. It does move, just less than the bug does. And the bug is not as hard, so it can't withstand the force that the car can withstand. And it's also, again, known as action-reaction. Now, Newton's second law is force, well, you can say here, it's the acceleration of an object is directly proportional to the force on an object and inversely proportional to its mass. So that just means acceleration is equal to force divided by mass. So you may also see it as, so we have a rocket with a mass of 0.1 kilograms is shot up with a thrust of 3 newtons. What is its acceleration? We have this equation that is in your reference table. Its acceleration equals force divided by mass. This is on page 6 of your reference table. And we can just plug it in right from here. We know that the mass is 0.1 kilograms and the force, in this case it's the thrust force, is 3 newtons. Thrust is just the force it takes for a rocket to go up. So we can then just plug this in. So the force is equal to 3 newtons and the mass is 0.1 kilograms. And we will get 30 meters per second squared. Now, something that we haven't talked about, this Newton, this is a derived unit, and it is a kilogram times a meters per second squared. And we can, if you ever forget what that is, you can always work this out. You can say that F net, or force, is equal to mass times acceleration. So mass is kilograms and acceleration is meters per second squared. And force is usually newtons, but that's what a newton is equal to.